stuff like we had in 4.1. And I don't like this room. I'll never turn off. Oh, we just use the other half of the building. All right, go over here. What I have on there for the definitions and stuff like that, I don't think that's going to surprise anybody, but let's talk about it anyway. We're talking about a function that's increasing or decreasing mainly. And that's a really bad function. So let's say we had a graph like this. We all know that this is an increasing function. This is a decreasing function on this side. And did I just turn off? It's like it's got this mind of its own. That was off. Each side will go off. Alright. That one went off. So we'll work with this. What's that here? So we know that when the first derivative is positive, that means that the slope is positive. That's an increasing function. When the first derivative is 0, you would have at that instant at least, it'd be constant. They're more talking about a flat function there. When the first derivative is negative, that means the slope is negative. That means that you have a decreasing function on that interval. So that's all those definitions mean. There's nothing fancy or tricky about those definitions. What I want to do is walk through this first example. We're going to go through this one really nice and slow for the first one. Because 4.3 really is all about this. 4.4 just builds on this. So if you have any questions with this first example, again, yell as we go through it. Let me go around here. So we do start with a rational function. Again, the word rational just means like you've got variables in the denominator. It says find the open intervals on which the function is increasing or decreasing. We're going to start off with the critical numbers. So as I said at the start of class, at least 4.3 really picks it up with a lot of stuff from 4.1. There's a lot of overlap there. So we are going to find the critical numbers, which is a lot of what we talked about in section 4.1. Now, critical numbers are where the first derivative is equal to 0 or the first derivative does not exist. But first of all, let's talk briefly about the domain. Because we do have variables in the denominator, we have to make sure, again, denominator can't equal 0. So x cannot equal 0. And so basically our domain is going to be all real numbers except 0. Everything else will go. Just 0 is the only number that we can't use. So 0 is not in our domain. We need to find this derivative. I'm going to go ahead and leave it as it is and use the quotient rule. You do have some options because you could, go through and reduce some of this if you wanted to first, but I'm just going to leave it as it is and just go through with the quotient rule. So we start with the derivative of the numerator, which would just be 1 times the denominator. And then next time we keep the x plus 4 and take the derivative of the denominator. and all over the denominator squared. And we're going to simplify this first. So multiplying out the numerator. In the numerator, I'll combine like terms. We have 1x to the fourth minus 4x to the fourth. All the algebra. And you can factor out the numerator. If you don't do it now, you would have to do it eventually. So maybe I'll just kind of leave it as is. We'll have to factor it eventually. But when we get to this stage, remember we're talking about critical numbers, and for critical numbers, we're looking at where does the function equal 0, and where is the function undefined, or the derivative undefined. The function will be undefined when x is equal to 0, which is also a point that's missing in our domain. I'll write that out, right? And again, x equals 0, we've already found is, a number that's missing in our domain. The other thing we want to do is, again, take the whole first derivative and just set it equal to 0. Now last week ago, a long time ago, a week and a half ago, I had told you could just set the numerator equal to 0, and that does the same thing. Because the very first step I would do is multiply both sides by the denominator. And say that again. I know last time we met, I had said that even though the directions say you're supposed to see where the first derivative is equal to 0, that's really the same thing as just saying set the numerator equal to 0. So if you want to skip that step, you can. You also want to check where the denominator equals 0, because that gives you these places where the derivative doesn't exist. And we keep on solving it. So now I'm going to factor it. So again, if you didn't factor over here, like I said, you're going to have to factor eventually. So to solve this, I want to factor it and set equal to 0. And then we just set each factor equal to 0. So I'm going to factor out a negative x cubed. But it does have to be factored and set equal to 0 before you can split these off into smaller problems to solve. Because then we set each factor equal to 0 and keep on solving. And you guys can solve each of those. That x equals 0 keeps on popping up. That's going to be the third time now. All right, so we've done a lot of algebra here, so let's pause. Questions with this so far, because we've taken the first derivative and really just been working with the first derivative right now. So questions up to here? See how far I've gotten on my list of things here. So number one, that's all I've done so far. Number one. Let's move on to part number two. So again, hopefully you can see that all we've done so far is really the same stuff that we're doing in section 4.1. And this is now where it gets different. We are going to take these numbers and take my real number line. That's going to represent my real number line, so from negative infinity up to positive infinity, or you can really call it the x-axis. And we're going to break that up using these numbers we found, which is just x equals 0 and x equals negative 16/3. And as long as you put them in order from low to high, don't worry about spacing or stuff like that, just put them on there. Again, this is representing the x-axis or a real number line, but it's representing from negative infinity to positive infinity. And what we're going to do then is just test each interval. And let me kind of over here explain the reasoning behind what we're doing next. And I'm going to use it with a really easy function, not that one. But again, this takes us back to some of the stuff we did in 4.1. It's not all new, but it's been a while since we did it. What we've done so far is we've taken the first derivative and we've set it equal to 0 and we solved it, or we looked at where it didn't exist. Those points that we just found, that's where it can change directions on us. And again, if it's a sharp corner, again, same thing, sharp corners just would do that instead. So that would be where the derivative doesn't exist. But those are the places we found so far. Those are the places where it could change directions. So now what we're going to do is check each interval and see, is the first derivative positive, or is the first derivative negative, or is it positive? Because if the first derivative goes from positive to negative, that means you've got like a maximum there. If the first derivative is going from a negative slope to a positive slope, that's where you're going to have a minimum there. So that's kind of the next phase of this. We're just going to check to see if the derivative is positive or negative. That's it, to see if it's going up or to see if it's going down. That's all that's in this step. So what we're going to do is pick some number that's less than negative 16/3. So anything this interval right here is representing anything from negative infinity up to negative 16/3. So you pick any number in that interval. I'll pick x equals negative 10 just because it's easy to work with. And all I want to know is the first derivative positive or is the first derivative negative? That's it. We just want to know, is it going uphill or is it going downhill? That's all we're checking for. So I come over here to where my first derivative is, and I just want to know again, is it positive or negative? So I take x equals negative 10, I plug it into the first derivative, and I would get, sorry, I got to look at it in factored form. Of course, you have calculators, you can stick it in and check. That would be a positive times a negative times a positive. Is that negative? I'm going to double check it with a calculator. And we do the same thing for each interval. And like I said, hopefully someone's double checking my arithmetic here. This interval right here represents anything from negative 16/3 to 0. And we just want to know, is the first derivative positive or negative? That's it. So over to here, I'm going to plug x equals -1 into this, and I would get a negative times a negative is positive, times a positive over a positive, 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 positive is positive. And again, you can use your calculators. You don't have to think everything through in your head. But you get, we're just wanting to see is the first derivative positive or negative, and that's it. So what I have so far is the graph starts off with a negative slope, and then right here it changes and there's a positive slope. And then it could change again at 0. We got to check it. So now I pick any number bigger than 0. So for simplicity's sake, I'm just going to use a 1. And I got to plug it back into the first derivative. So I come over here, I plug x equals 1 into this. I would get a -1 times a positive times, or over a positive, so negative. So, questions on this phase before we write out our conclusion? So, I know the first derivative was negative here. That's not what the graph looks like. It's not a straight line. But the first derivative is negative just means it's got a negative slope. It's decreasing. And then from negative 16/3 to 0, my slope was positive. It's not a straight line like that. And then from 0 to infinity, the slope was negative again. Again, that's not what the graph looks like. It's not a sharp, jagged thing like that. But let me write out my conclusion. Because again, the big picture that we're doing for right now, we're just trying to look at these things right here. So where is it increasing, where is it decreasing? So this is my final answer. So we want to know where the function is increasing. It's increasing when the first derivative is positive. If you prefer an equality notation, that's fine. But it's on that interval between when x goes from negative 16/3 to 0. And decreasing. And then the places it's decreasing, that's when the first derivative is negative. So from negative infinity up to negative 16/3. Also from 0 to infinity. So questions with that before I say one more thing? Probably just one more thing. Eventually, we're going to tie this back in with minimums and maximums again. Because if a function goes from decreasing to increasing, of course, there's going to be a minimum there. If it goes from increasing to decreasing, there could be a maximum there, or a local maximum at least, relative max. At this particular problem, again, 0 is not in the domain, so that would, it's got actually an asymptote going through the graph there. But it's all going to tie back in again eventually with those extreme values and stuff. Questions with this? I don't think we have time probably to do a whole other problem. So we'll stop